Hey everyone, and welcome back. Today we're going to tackle a concept that is the absolute bedrock for understanding how induction machines really work. We're talking about stator and rotor flux linkages. Now, getting a solid grip on how this magnetic flux is created and how it interacts inside the machine, well, that's the key to everything else, especially when we start talking about torque and control. All right, let's jump right in. So here's how we're going to break this down. It's a really logical, step-by-step process. First, we'll use a handy tool called the superposition principle. Then, we're going to look at what the stator does all by itself, and what the rotor does all by itself. And once we have those two pieces, we'll snap them together to build the complete, realistic model. Think of it like building with Legos, one piece at a time.
You know, inside a running motor, you've got currents flowing in the stator and the rotor at the same time, creating this big, complex magnetic soup. It's kind of hard to analyze all at once. So to make sense of it, we're going to cheat a little. We'll pretend only the stator is on and figure out its flux. Then we'll pretend only the rotor is on and get its flux. Finally, we just add the two results together. That's superposition in a nutshell, and it makes our lives so much easier.
Okay, for our first building block, let's imagine a really simple scenario. We're going to pretend the rotor is completely disconnected. It's open-circuited. That means zero current can flow in the rotor windings. It's just sitting there. Why do this? Because it allows us to focus only on the magnetic field that's being produced by the stator currents with no interference from the rotor.
This leads us right to our first major equation for the day. This expression here defines what we call the stator flux linkage space vector. We call it lambda s, for this specific case where the rotor is open. Now, not just stare at the symbols. Let's actually break down what these two terms on the right-hand side mean physically. This is where the real understanding comes from. All right, this distinction is absolutely crucial. The first term, the one with Ls, represents the leakage flux. You can think of this as wasted flux. It's generated by the stator current, but it just loops around the stator's own wires without ever making the jump across the air gap to the rotor. It doesn't do any useful work. Now the second term, with Lm, that's the magnetizing flux. This is the hero of the story. This is the good stuff, the useful flux that successfully crosses the air gap. It's what's going to interact with the rotor to produce torque. I can pretty much guarantee you'll see a question on your exam about the difference between these two.
Now, here's what's so cool. This diagram gives us a picture of the math. In our simplified world where the rotor is off, things are incredibly tidy. The vector for the stator current, the vector for the resulting magnetic field, and the vector for the flux linkage. They are all perfectly lined up. They're collinear, all pointing in the exact same direction. It's a nice, clean, direct relationship that we only get in this special case.
And hey, just a quick reminder on why we're even using these things called space vectors. Trying to track the currents or flux in all three phases, A, B, and C, separately is a real headache. The space vector is a brilliant piece of mathematical shorthand that combines all three of those separate quantities into a single rotating vector. It lets us see the big picture and simplifies the analysis a ton.
Okay, we've got our first piece of the puzzle, the stator. Now for the next building block. We're going to flip the script entirely. This time, imagine the stator is disconnected, totally open-circuited. Now only the rotor has current flowing. And the best part? We're going to apply the exact same logic we just used for the stator.
And, surprise, surprise, look at the equation for the rotor flux linkage. Does it look familiar? It should. It's practically a mirror image of the stator equation. You've got a term for the rotor's own leakage flux and a term for its magnetizing flux. The structure is perfectly symmetrical. Nature loves symmetry, and so do electrical engineers. And just like before, the diagram tells the same clean story, but now from the rotor's point of view. With the stator turned off, all the rotor's important quantities, its current vector, its flux density vector, its flux linkage vector, they're all collinear again, perfectly lined up along the rotor's own axis. Same principle, different part of the machine. All right, this is it. This is the moment we've been building towards. We've looked at the stator by itself. We've looked at the rotor by itself. We have our two fundamental pieces. Now it's time to put them together and see what happens in a real running motor when both the stator and the rotor currents are flowing at the same time. So remember these. On the one hand, we have the flux created by the stator currents. On the other, the flux created by the rotor currents. Now, as long as we don't push the machine's iron core into saturation, the principle of superposition tells us that to find the total effect, we can simply add the two individual effects together. It's really that straightforward. And this quote right here just nails the key takeaway. Those two magnetizing fluxes, one from the stator and one from the rotor, meet in the air gap. And what do? They add up.
Now, it's a vector addition, so direction matters, but the point is they combine to create a single net magnetic field in the machine. This interaction is the heart and soul of how the motor works.
And this leads us to the grand finale for the stator. Here is the complete equation. Now look closely. The first part is exactly what we had before, the stator's own leakage and magnetizing flux. But look at that new term added on the end. That's the mutual flux. That is the flux from the rotor's current reaching across the air gap and linking up with the stator. This is the coupling, this is how the two halves of the machine actually talk to each other.
And of course, for every action, there's an equal and opposite reaction. This same exact thing happens for the rotor. Its total flux is its own flux plus a new mutual flux term from the stator's current linking with the rotor. And there you have it, a beautiful, symmetrical, completely coupled model. We now have the full picture.
So let's put it all together in one place. This table is your money slide. Seriously, screenshot this, put it in your notes. It perfectly lays out the logical path we just walked through. We started with the simple, isolated cases, and we built our way up, step by step, to the final complete equations. If you can explain the story this cable tells, you've mastered this topic.
So we did it. We have the complete set of equations that describe the entire magnetic state of the machine. But that leaves us with the big, multi-million-dollar question, doesn't it? We have all this math describing these invisible magnetic fields. How in the world does that translate into a real, physical twisting force? The torque that actually makes the shaft spin and do work. How do we get from flux to force? Ponder that for a bit, because that's exactly where we're headed next time.
All right, welcome class. Today, we're going to dive into one of the most fundamental challenges in advanced motor control. The big question is, how do you mathematically model those complex, chaotic magnetic fields swirling around inside an induction machine? You know, getting this right, it's the absolute key to unlocking high-performance control. So we're going to tackle this with a really clear game plan. First, we'll lay out the core problem. Then we'll introduce this powerful divide and conquer strategy. From there, we'll build our model piece by piece, first the stator, then the rotor, before finally putting it all together to get to that master framework that really every modern motor control system is built on. Okay, let's dive right in. Our first step is to really appreciate the problem we're up against when we try to look inside a running motor. So what you see on the left, that's what's actually happening. It's a tangled, chaotic mess of magnetic fields all interacting at once. Our job as engineers, though, is what you see on the right. We have to turn that chaos into clean, precise math, into space vectors that we can actually use to control the machine. So, the big question is, what tool do we have in our engineering toolbox that can possibly bring some mathematical order to all of this magnetic chaos? And the answer is a truly elegant strategy, one we borrow from fundamental circuit theory. It's called the superposition principle. And it gives us a clear three-step roadmap to solve this whole problem. Our strategy is actually beautifully simple. First, we're going to look at the stator all by itself, as if the rotor doesn't even exist. Then we'll flip it and do the exact same thing for the rotor, ignoring the stator. Once we understand each part in isolation, we'll combine or synthesize our findings to model the complete, real-world system. Okay, first up, phase 1. Let's basically freeze the system and look only at what the stator's magnetic field is doing. So our first move is to impose a simplifying condition. Just imagine the rotor currents are zero. They're just not there. This makes everything so much easier because it lets us define all our magnetic vectors relative to one single stationary reference point, the axis of the stator's A phase. And really pay attention to the notation here. We're using a lowercase a as a superscript. Trust me, this is going to be very important later on. Now, we need to break down the total stator flux. See, it's not just one thing, it's made of two critical parts. First, you've got the leakage flux. That's magnetic flux that basically just loops around inside the stator. And second, there's the magnetizing flux, which is the useful stuff that actually makes it across the air gap to do work on the rotor. So here is the crucial point, the key insight. In this isolated, super simplified state, all of our stator space vectors, the current, the flux density, the flux linkage, they all line up perfectly. They're all collinear, pointing along the exact same axis. This is a massive simplification, and it's what makes this whole analysis possible in the first place. All right, let's switch gears. We're now going to apply the exact same logic to the rotor, but as we're about to see, there's one critical difference we absolutely have to account for. So for phase 2, we do the opposite. We set the stator currents to 0 and focus only on the rotor. Now, pay close attention to the notation again. See that? It's an uppercase A superscript now. That's a huge clue. It tells us that our new reference frame is physically attached to the rotor's phase A axis. And because the rotor is physically spinning, this frame is rotating at an angle, data m, relative to the stationary stator. You know, this equation should look really familiar. It's the same idea. Just like the stator, we build the rotor's flux linkage from its own leakage and magnetizing parts. And, just like before, as long as we analyze the rotor by itself, all its field quantities are also perfectly collinear. But this time, they're collinear within their own rotating reference frame. Okay, let's hit pause for a second. We've looked at the stator in isolation and the rotor in isolation. This is a perfect checkpoint to just summarize what we have before we try to bridge these two systems. This table lays it all out pretty neatly. We have two separate systems, two distinct worlds. The stator system is stationary, and we use that lowercase a superscript. The rotor system is rotating, using the uppercase A superscript. Each has its own simple governing equation. Now, the mathematical bridge that's eventually going to link these two worlds, that's the mutual magnetizing inductance, LM. Now for the most important step, the synthesis. We're going to combine these two worlds and see what happens in a real motor, where both the stator and the rotor currents are flowing at the same time. Okay, the crucial point is how we write this new equation for the stator flux. The first part, Ls times Is, that's the self-induced flux we already know. The second part, Lgim times Ir, that's the new piece. That's the flux that's mutually induced onto the stator by the rotor's current. But look very, very closely at the superscript on that rotor current term. And there it is. That rotor current has a lowercase a superscript, not the uppercase A we defined for the rotor's own frame. So what does that tell us? It tells us that, to calculate the total stator flux, the rotor's contribution must be described from the stator's stationary point of view. And that presents a major mathematical challenge. And this visual just illustrates the solution brilliantly. You simply cannot add vectors that exist in different coordinate systems. It's like, think about this. If you're trying to describe a person walking on a moving train to someone standing on the ground, you can't just tell them the person's walking speed, right? You have to add the train's motion to it. We do the exact same thing here. We have to mathematically project the rotor's vector from its rotating world onto the stator's stationary world. And to calculate the rotor's total flux, well, the exact same logic applies, just in reverse. We take the stator's current vector, S, and we perform the inverse projection. We have to describe it from the rotor's moving point of view. And that's exactly why you see the stator current term, S, now has that uppercase A superscript in the rotor's flux equation. So after all that careful work, isolating, analyzing, and transforming, we've finally arrived. We've reached the master framework. These are the final equations that really form the toolkit for every single advanced drives engineer. And here they are, the master equations. On the left, you have the total stator flux linkage, calculated in the stationary frame. On the right, the total rotor flux linkage, calculated in the rotating frame. Together, these two equations give us the complete picture. They perfectly describe the magnetic state of the machine, accounting for both self-induction and that crucial mutual interaction across two different reference frames. You know, this quote just captures the essence of everything we just did. In the real world, that simple collinearity is gone. But because we used superposition to break the problem down and then mastered the frame transformations to put it all back together, we've gained the tools we need to build those sophisticated vector controllers that can precisely control an induction machine. And this, of course, naturally leads us to our next big question. Okay, we have a perfect mathematical description of the flux, but how do we translate this deep understanding into direct, instantaneous control of the motor's torque and speed? Well, that is the very heart of vector control, and it's exactly what we are going to explore next time.